one, because one of the things that we've sort of a bit right. If you need, I'll have a good.
Okay. Louise, do you want to start your many slides?
My many slides. Yeah, so this is a discussion session on radial velocities of young stars, or more importantly, how to get masses of young planets. I guess it's sort of open-ended how long we have, but I suggest we don't spend too long. I'm getting a very low energy vibe, mainly for myself.
Have you seen the questions? I don't think we're.
Let's see, but yeah, I think if some point if people really wants to to stop, then just go right. Yes, my name is Louise Nielsen. I work for ESO at the moment. And I did the world's shortest postdoc with Suárez of 9 months. Anyway, so we have a problem. Young stars are very active. And that's a problem if you want to measure the masses of the planets that are around them. It's probably very interesting if you're interested in the stellar physics of stars and young stars. And I think all of the talks that we've heard the second half today have been very good at sort of explaining the magnitude of that problem. So I'm not going to go too much into detail what the issue is. I do want to show that this is data of ds-tug-A. And this is just some simple animation where you put some spots on the surface of a star and then just look at how you can fit the photometry. But I always like to ask my audiences. The results of this animation over here is the black points, and then the blue curve is the actual photometry from tests. And then I always ask my audience members if they can find the planets. You can get a few minutes. But there's a planet transit here. And there's another planet transit here, but the data is pretty crap there, so don't worry about it. Anyway, so we can fit that photometry with a nice GP or whatever, and then get a nice transit out of it. So that's the photometry part of the problem, and I'm not sure if we fixed that part of the problem either, but of course what we're talking about today is radial velocities. So here I show an example of K2233. That has 3 planets around it, and we're very lucky because the planets are transiting, so we know the period of them. And each of these planets have a radial velocity semi-amplitude of around 5 meters per second. But we also see the stellar radial velocity amplitude of 30 meters per second. So what you see on the top here is the raw RVs in red, and then the GP model plus the 3 planets on top of it. And then on the bottom, we kind of zoom in and remove the GP model from the data, and then plot just the planets. So this is sort of the scale of the issue, is that we have way more signal from the star than we do from the planets. So of course, it's not like we're not measuring the masses of young planets, as we've heard today. So I've sort of tried to throw in some of the good examples of how we're still going after these targets, because scientifically they're of great interest. But it's extremely expensive, and I find a little bit from my side of things is that, and I have this as a question later in the discussion, it's how do we convince the rest of the community, or when we apply for time with ESO, for instance, how do we justify spending so much time on one star, for instance, to get maybe an upper mass limit or mass for 1 or 2 planets in the system. So it's extremely expensive, and this is sort of what we're gonna try to discuss today, how to get better at it. I was gonna say something about this. Whatever. Okay, so I have a few slides on what I think could be a part of the solution, and it's highly biased towards what I'm interested in, and that's near-infrared spectroscopy. So I'll just go into this a little bit, but then afterwards we will open up to other parts of the solution. All right, so our problem is that these young stars are active, but one of the solutions is that they're less active in the near-infrared. So here you have a star in near-infrared color, everyone can see that. And then over here you have the visible.
That's not how it works.
I spent a long time deciding on this infrared color. Anyways, but the idea is that the contrast you have between the surface of the star, the continuum, and a spot would go down when you go to the near-infrared. And if we assume that young stars are mainly dominated by activity in the form of spots or dark spots on the surface, then you have this nice thing that when you go to the near-infrared, then you'll see less activity. And this is also what people have been used in terms of looking for these chromatic activity variation that the activity signal from the star will be wavelength dependent, and the Keplerian signal of a planet is not. So hopefully that's fairly known to people. Of course, this has been tested and shown in quite a few different ways. This is a young star, AD Leo, that has been observed with the Carmenes and the GAPS project that we heard a little bit about today, where in blue we have radial velocities from the visible part of the spectrograph, and then in red you have radial velocities from the near-infrared part of the spectrograph. And as you can see, the blue ones face up really nicely, so this is a phase-folded plot. And the near-infrared don't. So this is actually a case where they have refuted the existence of a planet, showing that this very nice phase radial velocity variation you see is due to stellar activity and not due to a planet. Let's see, there's also a really nice poster of sort of comparing optical and near-infrared RVs on our poster channel for this workshop. And then, of course, there's some work done on this chromatic index, also here again from the GAPS project, where the idea is that you compute radial velocities for each of the, let's say, the orders in your spectrum. And then if you see this, like, so this is for two different epochs. And then if you see some kind of variation or change of the velocity that you're measuring as a function of wavelength, it's late in the day. All right, so hopefully this is fairly known to people, but it's good to be on the same page. All right, so of course the solution to this problem is called NIRPS, and it's a near-infrared spectrograph that's going to join HARPS on the 3.6 meter telescope in La Silla. So the idea is that HARPS and NIRPS will be operating simultaneously, so you'll get spectra from both of them for all of your stars if you want to. It's going to have a resolution of 100,000. I actually have to double check that number because it's still work in progress. But the goal is to reach a 1 meter per second RV precision, which is something, to my knowledge, we haven't really been able to do with near-infrared spectrographs just yet.
And there'll be like a dichroic, and it feeds the two spectrographs at the same time.
Yeah, exactly. Yeah. So sorry for a second, I thought you meant inside the
No.
Yeah, so we're combined with HARPS, it will have this wavelength range from around calcium HK till the near-infrared at 1.8 microns. We have a bunch of different wavelength calibration options, but I think the working option at the moment is a Fabry-Perot, and then we'll have like some uranium neon for data calibrations. A really nice thing or cool thing is that it's going to have an AO-assisted fiber on sky, so we'll have this 0.4 arc-second fiber to put all the light into the spectrograph, and that's sort of how we can leverage still getting a good resolution, even though that the wavelengths are longer. And then it just arrived in La Silla like last week, so this is why we're very happy at the moment. Boom. All right, so we're going into the discussion side now, so I'm not going to speak too long. But how I see both defining what the issue is, but more importantly, of course, how we're gonna move forward as a field in how to deal with these stars. I see 3 different areas, and one of them is observing strategy and data reduction. We heard a little bit about the data reduction today. We talked quite a lot about sampling. Then there's how we model the stellar variability. So let's say GP kernels, or are we gonna operate on a 2D spectrum level, for instance? We also discussed quite a bit. And then I put the rest into like stellar physics plus, but really everything else. And then now I'm gonna go to my last slide, and it has a lot of text on it and a lot of questions. And the idea is that we are gonna go through all of them, but I thought we could like sort of start with one thing that we think is interesting, and then we can take it from there. Yeah, so I don't know if anyone wants to. I haven't figured out how to transition it to you guys just yet. But trying to. Yeah, Susanne, thank you.
So I have a sort of comment which is sort of partly response to several of your questions. But so you mentioned that it's really expensive in terms of telescope time, and it can be hard to convince tax to give you enough time. And I think that we have the tools now to do lots of simulations and to prove that if our assumptions are correct, a particular amount of time will allow us to do a certain thing. It only works if the community uses this in a this or other approach, but does this in a consistent and honest way. Because if a TAC receives 3 proposals and one of them asks for half of the time of the other 2 to do the same thing, it's appealing to give the time to the people who say they will be able to do it with half the time. But one possible argument that we could try and make as a community, if we really want to dedicate significant amount of time to these very young stars, aside from the fact that they're interesting in themselves, is that it's an ideal test bed for the techniques that we need to develop in order to find Earth, etc. But then I ask myself, how far can we push that argument? Because we've, several people today and on Monday have shown that we can get actually to an astonishing extent below the stellar noise for these super young stars. And if we could do that for the sun, we would be in an extremely good position. But I'm not sure we can, because the sun is much less active but much less coherent than these stars.
Yes.
So that's kind of the other question on my mind, is whether we will end up with strategies that are qualitatively different for these very young stars compared to more stellar stars.
Yeah, I think it's a nice question to start with. I've kind of sort of have it here as other lessons that we can learn from working with very active stars and find rocky planets in 1-year orbits. Let's start with Belinda.
So one thing that I noticed is missing from here, and I think this is perhaps a way of being able to, sorry, I'm going to take this down so people can hear me better. One way that we can perhaps justify a lot more time is if we're getting a lot more than just a planet mass out of our observations. And by doing this, I'm going to advocate that whenever we're doing radial velocity measurements for young stars, we need to be doing them in polarimetric mode. So having the spectropolarimetric information, you get your longitudinal magnetic field, you can map magnetic fields if you're sampling them correctly, and you're just getting so much more information about the star. And there is still so much that we don't know and don't understand about the magnetic fields of young stars. We don't know how the dynamos evolve. There's just so much information there that we don't have yet, that if you're wanting to sell it to a TAC, that you need a whole lot of time to do these observations. The more science you can pack in there out of the one data set, the better. So I'd be advocating that whenever you're going to observe a young star with spectroscopy, do it in polarimetric mode and get all of that additional information at the same time.
Staying with back, Vincent.
So I like Suzanne's point. I mean, I guess the argument of saying we should do young stars, because that might help us choose which, for example, which GP kernels to run on other stars as well, and that might help. But are you kind of suggesting that it may not help because, in fact, maybe it's easier for young stars because they're so active, so we can actually detect the activity so much clearer, so we can actually train our models a lot better. And for the less active stars, paradoxically, we don't have the same amount of information, so it's actually harder to do. Is that kind of?
I think we can use the young stars to validate some of the models and methods that we've been developing, because the signals are so much clearer and they rotate faster, so we see the line distortions much better, as we saw in Claudia's talk. And so there's a lot of things that where the activity signals are much easier to access, and therefore we can use them to test our methods. But so within the terra hunting experiment, for example, I have been advocating for not placing a cut on activity level, because when we select our targets, and there's multiple reasons for that. One of them is that I think that has subtle bias implications for like the ages of the stars we're looking at and various other things, which I wouldn't feel comfortable about doing unless we understand these biases. But the other reason was that I wasn't convinced that it's easier to correct, to get, like, what we care about is the final sensitivity in terms of planet signals. And I'm not sure it's easier to detect an Earth in a quiet star, then in a slightly more active star, so I think there might be a sweet spot, or there might be the opposite of a sweet spot, a sour spot. What would you call it? Because it's kind of, if the star is really active, we can model the activity really well, and these young stars tend to have long-lived spots, really stable. And then if the star is really quiet, activity is less of a problem. And actually, maybe you've got something in the middle where moderately active stars are our worst nightmare. So.
Yeah, Alejandro?
There's I think, I don't know if the problem is the word, but there's a difference a bit between what we are doing or trying to do in the young stars and then what we are trying to do in the solar type stars. Is that for the most part in the young stars, we only go for transiting planets because there's almost no way we can get anything in a blind search in any of those. Whilst on the other ones, we're going for the blind search, which I think makes things completely different and difficult to compare to each other.
Yeah. Jen, did you have your hand up before?
Yeah, I have a question because I don't think about very active stars very often. Is the assumption that even though they are spot dominated, there is still this like 1 meter per second faculae induced floor to them? Or is it if you correct the spots, then you've fixed, like there are no faculae strong signals, so you've gotten below 1 meter per second if you do the spots very, very well?
You don't, for the convective glow shift inhibition, you don't really expect this to play a role here because these stars, like very young stars, are mainly, well, even fully convective. So these kind of things are definitely negligible. What you can expect, especially if you go to the infrared, is to start to have the actual Zeeman effect to play a role in the RV. So what we see, for example, for IUMIC, you go invisible, you see that you have extremely strong variations that are clearly due to brightness contrast. But if you go to the infrared, you see an extremely strong correlation between your magnetic field that you can measure in the infrared from the Zeeman broadening and the actual RVs. So it's quite interesting. We don't really know why we are so much sensitive in the infrared to this. We expect to be more sensitive to, but yeah, this is these two effects that we
Well, we don't know the floor.
But
We don't know if it's 1 meter or less.
But-
We don't know.
Or high.
We don't know for these stars. We
Yeah,
just have
there's a
to-
flaw, but we haven't found it yet.
But we should also be limited by just rotational broadening at some point.
Yeah.
The lines are too wide that you cannot really get to less than 10 or 15 meters per second.
Depending. We have a down here.
Just on this, we should be careful there because I never saw an active stars where the residuals in terms of air mass was 1 meter per second. So then we cannot, I think, make any assumption of this. Then you had this question about like it's very difficult to get time and so on. I think we are still in a mode where each group here and there start like applying for time and say, okay, I want this amount of time for this active star because my science is super interesting. And then the OPC at ESO or whatever, or the telescope, they receive 10 or 20 proposals like this. What we should do, I think, is like write a white paper, the community, say that this is what we have to do and we have to get a lot of telescope time for that. And then rather than sending 10 proposals or 20, we should send one with 100 people, but it would be one. It would be a community-focused effort and not like single group if we really want to get this through. Otherwise, it will not work.
I think Louise should write.
Yeah, we are ESO.
And no, but also I think, and then you make the data public. And then encourage everybody to play with it.
Yeah, because the thing is that these are so tricky targets to work with that it's fine to have someone else wanting to publish something on it as well.
Can I say, people, please do try to break our AUMIC results. Go out and test it. The data is there. Go out and test it. Let's see what other people find. This is what we found.
Yeah, related to that, I know there are some apprehensions about using multiple different instruments, and I'm very cautious about it. I only use my one infrared spectrograph, but it's easier to get time when you're like, I have a bunch of data at another instrument, but I want to check it in the visible. I want to get photometric coverage. I want to recover this in somewhere else with a different instrument at different stability, et cetera, et cetera, et cetera. I think it's easier to convince. So please add me onto your telescope proposals. I have a bunch of young star data in infrared. Please add me.
I just wanted to say the obvious thing, which is that we think that planetary systems evolve in non-trivial ways in the early stages of a star's life. So forgetting about the activity question, it's genuinely extremely important question in planetary science,
Oh, yeah.
exoplanets, to understand the populations of planets of young stars. And even if our sensitivity is lower, there are respects in which we can more or less directly compare the planetary systems of the younger stars with the older stars, and that is just so critical to understanding what's going on. There's all these fairy tales about our own solar system formation, which I frankly cannot believe. But if they're true, then there must be amazing things going on with these stars.
Yeah, and I think, sorry, I'm gonna cut in, but then we'll get to you, Alejandro. I had this question somewhere, like, do we need simultaneous photometry? And I was very inspired by Alejandro's talk. Remember, I think also for some of, for instance, like ESO proposals, there are smaller telescopes where you can apply for simultaneous photometry as well, or it's something that is available in the community. And I think that is also something that can help us getting the telescope time on the larger telescopes, if we can show that we're being economic with the large telescope time we get, like that we actually thought about also supporting it with smaller facilities. Alejandro?
Yeah, I just wanted to comment that when I said that mixing different instruments was painful, I was not saying don't ever do it. Just you can avoid it, but I know we can't avoid it. It's just what's going to happen and we are going to do. And about the collaborations, I would just want to point out that we've only been able to work on V1298 Tau because we collaborated with the people at Potsdam and with the people at GAPS. Without them, we would have never gotten the half of the data, or not even half of the data. So these kind of projects really need as much as community together as possible.
Why is this that?
Following up on the question about quasi-simultaneous photometry and or multiple instruments, there's two things that come to mind. One of them is that, so the Plaftown group is not represented here today, but they have tried to do a chromatic GP model.
Yeah.
And I would say it's still a work in progress. And it's an interesting question whether you expect the activity functions to be qualitatively the same in the infrared and in the optical, but it's an interesting area of work. And I think the reason you expect they might not be the same is because of the faculty to spot ratio and because of this Zeeman splitting question. And the other thing is, I gave a talk at MIT last fall, and I was approached afterwards by people from MIT who are working on a proposal for a space-based photometry, small, like CubeSat type thing. And the purpose of it is to get continuous or near, photometry in support of radial velocity observations. So I don't know if people are aware of this, but this is an idea of sending one or more CubeSats so that you can do continuous monitoring of interesting targets. And it won't, it will be less precise than things like KOPS or TEF, but it would be plenty good enough to provide the activity indicators we need.
Yeah. And it's one of those cases where it's nice.
Gabor Faresh was the person.
But it's not a CubeSat. Now we are going for something.
It's a mid-X now. It's a small complete mid-X. But
it's a what, sorry?
It's an $80 million mid-X now.
Oh, is it? Oh, sorry, I'm completely out of date. Okay, so
we got ambitious, and now it goes from the near the UV out to the near infrared, and
okay, so it's
a lot of bells and
grown
whistles.
in scope a lot.
Oh, even better.
Okay.
The proposal is into NASA.
There will be a UV mission from Israel that will fly in a couple of years, Ultrasat, that I think can be used and applied to.
Vincent.
So on the observing strategy, but not the photometry, but just, how many RV points you really need, and particularly also how to spread them out, whether, things scale very non-linearly with sort of like how many data points you need. Unlike for very quiet stuff where you could sort of make some argument, square root n of some kind at least, it feels very difficult here to understand. And I suppose to start responding by the white paper, I think one thing that might help out convince time allocation committees is clarity on the argument of what it is you really need and whether things will really work when you then get that amount of time. Because it's very difficult to know sometimes, whether someone with 50 data points or 100 or whatever, 200 can do things. And it depends a lot on, it's not linear. It's not like with 50 data points, you can do half of the work you could do with 100. Or it's not with, having them spread randomly, you cannot do the same as having a bunch of highly sampled over a few nights. So making that point clearly somehow, and maybe we don't have the answer, like what's needed, but clearly showing if we get this kind of strategy and this kind of number of data points, we will be able to reach these things. I think will help a lot in convincing skeptical allocation committees that things can really get done when you then give that amount of time. And the problem is that sometimes people write proposals where they maybe make claims that then don't work out. Right? They get data points and it's just very hard to use them when there's not enough data or not sampled in the right way.
So I think I completely agree. So, over the last few years, we've written a few proposals where we do these simulations. So Oscar's written this tool that enables us to do simulations. So we take whatever data already exists on a given target, and then we simulate, and we fit that data to get some idea of hyperparameters, and then we simulate future observations, and we model them using the same model we would use. So, and then we try and see, well, if we got 30 more or 60 more or 90 more, whatever, how many do we need to get a secure detection? This is vulnerable to the criticism that you are generating observations with a model and then typically fitting them with the same model, right? So that's a feedback that we have sometimes got. But the other one is that typically what you find out is you need way more than you think you do. Yeah. And so you end up asking for huge amounts of time, and then the tech are like, well, that's really risky. And you don't have time to make the argument or space to make the argument very convincingly in a 2-page proposal. And so one thing that might be worthwhile is writing a white paper, because then you have the space and the time to make that argument coherently in a general context, or not for a specific target, but and then the community more generally could refer to it in proposals.
Yeah. Is there a view there on how reliable? I mean, do we know whether when these simulations predict a certain number of data points that actually turns out to be correct?
So part of the problem is new planets have a nasty habit of appearing. So I would like to say that we did this for EUMIC, and then we can tell you whether the answer was right. But in the meantime, we did it with one planet, and then there was a second one. And also EUMIC was at least twice as active when we observed it than when TESS first observed it. So that made it slightly harder to use our experience as a test. And all the other times we've done it, we haven't got the time, so I can't say. But
maybe we need to.
It wasn't that far off, actually, I would say.
For more quieter stars, we've done it in Espresso a few times in the GTO, and sometimes the simulations have been like much more negative than real life. Sometimes much more positive. It's really difficult to exactly predict what the star is going to do.
But it's also a little dangerous, I think, that then we sit down, we simulate how many observation points we would need. But then if that number is too big, then we dial it down, right? Like it's difficult to be very, very transparent while also maybe not really trusting the output that we get.
I mean, I shouldn't say this out loud, but in the future that I want, the amount of data you get will, like, your performance will scale with more data, because you'll be able to refine your latent models of the star. They will refine more as more data comes in. And so I think in the future that I want, you do better than square root of n, because as you go on, what happens is you understand the structure of the latent space better as you go. So you do better than square root of n, which would be great to show. But I do think it's going to be expensive, and you're not going to know until you're underway what performance gains you're going to get, because it's going to be things that violate our expectations. I think if there's one thing that has been a theme of this 3 days, it's that the stars are violating our expectations.
It's the reason why we have to observe them in the end. All right, so I have some, I included some questions about what we can learn from transiting systems. So sort of trying to a little bit refer back to the point that Alejandro made early on, that I think the reason why we're getting these young systems at the moment is because TESS is observing a lot of stars that are fairly bright and have found some young transiting planets that are easier for us to observe at radial velocities. So I listed two questions here. I'll read both of them out, and then we can see which ones we want to discuss. But my one question is, what can we learn from these easier transiting planets that we can then apply to, let's say, radial velocity surveys of open clusters or something to find more young planets that are not necessarily transiting. And then the other one, and I thought a lot about this during the discussion on using the 2D spectra, basically. And I was thinking a lot about how practical it is for doing a global model where you're analyzing your transit photometry, maybe some simultaneous photometry to your radial velocities and your radial velocities, how practical it would be to actually having to model the RVs in a 2D spectrum level. I don't know if anyone have like ideas or like a feeling for how tricky that is. I'm a little scared of it. Yeah.
If you go to very young stars, you agree that your vicinary is very large. So at some point, your RVs, you will not have a good precision on your RVs, no matter what you do. But this is where you need to start looking at the spectrum level or the line profile level, because this is where rotation-dominated things, like if you go to chromospheric lines, just to study what's the activity happens, or if you go to the full CCF or something like this, then you might be able to apply like Doppler imaging-ish method, and that can be pretty interesting in this case, I think.
I think it's true. We'll all have to learn Doppler imaging at some point.
There is a story, you know.
Things are getting easier. Hi, Alejandro.
Yeah, going a bit into the topic of the transiting planet, I think a problem we are having right now is that if I didn't miss any big group of discoveries, we don't have enough young planets from the transit surveys to do like any kind of reasonable statistics about anything. And as far as I know, what's happening is that TESS and Kepler K2 before have been detecting way less than expected planets in young clusters, which probably means it's already really difficult to get them in the light curve, and we are just needing to go light curve by light curve, the same we do with the radial velocity. So probably the first thing we need is better techniques to extract all the planets that we have in the transits and we are missing.
I completely agree. I think, I think there's one thing is hot Jupiters around young stars seem to be rare. And those are, would be far easier to find and to follow up. And there's just one, as far as I know. 2?
1.5.
Yes.
One with a mass and one.
Yeah, one with a mass and one without. And then the other thing is, yes, I think that we may be missing some planets because most of the ones that are found are essentially found by eye. And I know that Ed Gillen in Queen Mary is working on looking for more and doing it in a more systematic manner, using TESS and GTS data. And then so in Oxford, we've been running this Planet Hunters TESS project, and we want to put a special kind of workflow in it for young stars, because we think that if we're going to find them by eye, then more pairs of eyes wouldn't.
Yes.
Yeah. I think this is also a thing, the time collaboration.
Yes.
So Adam Krauss and Elizabeth Newton and Benjamin are like, they're, I believe, working from, can we identify stars that we think are in young moving groups or young associations, and then search them specifically for.
And that's exactly what we're doing.
Same idea.
Yeah, we have a group doing the
Do you have a hand down here?
Maybe they should.
I think that for young stars, obliquity.
The stars where we are finding, everyone is finding planets.
Because they're fast rotator.
Extremely well behaved in the light.
Time effect and so on.
Some of the young stars, it's like, it's horrible. Absolutely horrible.
They're young.
Yeah.
And so I think it might be within reach of the instrument, even while it is.
I think so far there's one target that has measured it with a young planet as well. At a point, I forgot it. Too late in the day. Yeah, actually, I think we more or less came through like all of the themes at least. So I think if anyone else has anything they want to.
I'm going to throw one.
Yeah.
Flares.
Oh yeah, that was something I had wanted to mention for AUMIC. Yeah, so for the AUMIC, when we were going through the HAPS time series, there were some very obvious outliers by several hundred meters a second. I'm looking at you, Baptiste.
Sorry.
Well, you can see definite emission in H alpha. And also
In the chromospheric lines, but it's all systematically detected in the chromospheric lines. So basically, it's the best way that you have without simultaneous photometry to spot flares.
Yeah. So it's exciting getting spectra of flares, but it's something that we basically just had to remove from the analysis.
But they weren't obvious in the raw time series because the activity signals were so big. So there were clear outliers in the residuals of the activity plus planet model.
Yeah.
But then we wouldn't have picked them out to start with.
My understanding is that H alpha is very sensitive to flares. So is this the case or not?
Yes. It is like most in H alpha, H beta, CH and K. It's a bit complicated because it's an M graph, so like, and yeah, mostly H alpha and H beta, basically.
So just using H alpha, you can remove all of them and that's it? Or you are still left with some things that you are not able to resolve?
I basically combine all the chromospheric lines that I have and like identify them, and I don't see any weird fluctuation that I cannot identify so far. But I cannot see the flares in every line for every flare that I flag. I cannot see the flare in every chromospheric line. Sometimes I don't see them. But it's not true for H alpha. I see them systematically.
Yeah, so if you only had H alpha, you would have identified the same
Yes,
flares
I
as
think
we
so.
did from.
Yeah, no, I had one comment on the, sorry, it's completely different. In terms of, alright, so we're not there yet where there are enough young transiting exoplanets that we could really do a big statistical study on it, but there are still transiting young planets that doesn't have a mass that are bright enough to be observed. So I think even though that we would have to improve on the photometry side of things, it's really the radial velocity side that is lacking at the moment. All right, I think otherwise we should release ourselves to the wild a little bit. All right, thank you very much. Yeah, if anyone wants to keep continuing discussing young stars or anything, then I'm very happy. And also, if you're interested in knowing more about NIRPs or infrared spectroscopy, I'm here all week.